Hi, for mini project PHY3306 presented by me, Nurul, Atikah, Farhanah, Binti, Abdullah. My metric number is 209042, and Muhammad Aqil Irfan bin Masnore, metric number 206738, and last one is Balqis Binti Ismail Rani 207782. For our mini project assignment, topic is operational amplifiers, or we call op-amps. So this is a presentation of operational amplifiers outline. The first one we have introductions of op-amps. The second one we have identify ways op-amps are used. And the last one is how they are wired in order to perform the operations. So my part, I will talk about introduction of operational amplifiers. So operational amplifiers are linear devices that have all the properties required for nearly ideal DC amplification and are therefore used extensively in signal conditioning, filtering, or to perform mathematical operations such as add, subtract, integration, and differentiation. So, an operational amplifier, or we call op-amp for short, is fundamentally a voltage amplifying device designed to be used with external feedback components such as resistors and capacitors between its output and input terminals. These feedback components determine the resulting function or operation of the amplifier, and by virtue of the different feedback configurations, whether resistive, capacitive, or both, the amplifier can perform a variety of different operations, giving rise to its name of operational amplifier. So, an operational amplifier is basically a three-terminal device which consists of two high-impedance inputs. One of the inputs is called the inverting input, marked with a negative or minus sign. The other input is called the non-inverting input, marked with a positive or plus sign. A third terminal represents the operational amplifier output port, which can both sink and source either a voltage or current. In a linear operational amplifier, the output signal is the amplification factor, known as the amplifier's gain, multiplied by the value of the input signal, and depending on the nature of these input and output signals, there can be 4 different classifications of operational amplifier gain, which is first we have voltage. We have voltage in and voltage out. Second, we have current in and current out. Third, we have transconductance, which is a voltage in and current out. The last one is transresistance, which is current in and voltage out. So that's all the introductions, operational operational amplifiers for me. So that's all. Thank you.
Good afternoon. My name is Muhammad Aqil Irfan bin Masnore with metric number 206738, and I will continue to talk about how op-amps are used. Op-amps are used in wide application electronic, and I have listed a few of its applications such as voltage follower, charge differentiation circuit, and current to voltage converter, to name a few of it from the list. And from this list, this is only a few from many out there. So we will look and talk about a few of it. Namely, first, the voltage follower. It is the most basic operational amplifier circuit. The circuit does not generally require external component and provide high input impedance and low input impedance, making it a useful buffer. Because the voltage input and output are equals, change to the input produce equivalent change the output. So we can write it as V out equal to V in. Next, we will talk about inverting op-amp. Op-amp forces the negative terminal to equal the positive terminal, which commonly ground. Therefore, the input current is determined by V in over R in. By looking at the diagram, we can see it. In the diagram, the same current flow through RF to the output. Ideally, current does not flow into the operational amplifier negative terminal due to its high Z in. The current flow from the negative terminal to R2 creates an inverted voltage polarity with respect to V in. This is why these op-amps are labeled with an inverting configuration. And the op-amp's output can only swing between its positive and negative supplies. And to prove, or if you want to calculate about this operational op-amp topologies, we can use the formula V out equal to negative RF over Rn times to V in. Lastly, the last example is voltage comparator. So it is an operational amplifier. Voltage comparator compare voltage input and drive the output to the supply rail of whichever input is higher. It is considered an open loop operation because there is no feedback. It also has the benefit of filtering much faster compared to the two previous topologies that we have discussed. And last, I will talk about how to choose an operational amplifier for your application. If you want to use it, you have to consider a few things, or three things. First, choose an op that can support your expected operating voltage range. This version can be obtained by looking at the amplifier power supply voltage. Next, you could consider the amplifier GBP. If your application needs to support higher frequency or requires higher performance and reduce distortion, consider op-amps with higher GBP. Last but not least, consider the power consumption. One should consider the power consumption, as certain applications may require low power operation. The recommended power requirement can typically be found in the part datasheet, where they usually list as supply current and power consumption. So that's all from me. Next, my group member will continue it.
Okay, thank you, Atikah and Aqil. I will continue the presentation with how operational amplifiers are wired, or the other names I will use as the requirement of operational amplifiers. Alright. Okay, so for the first one is offset nulling. So the offset nulling method is used to make the output to zero voltage. So most of the op-amps has an offset voltage at the output, even if the input voltages are the same. So in most operational amplifiers, there is a small offset because of the inherent property and results from the mismatches in the input bias arrangement. So a small output voltage is available at the output of some op-amps even if the input signal is zero. So this drawback can be rectified by providing a small offset voltage to the inputs. So this is known as the input offset voltage. So to remove or null the offset, most op-amps have two pins to enable the offset nulling. So for this, a port or preset with a typical value of 400K should be connected between the pins 1 and 5 with its wiper to the ground. So by adjusting, the preset output can be set at 0 voltage. Right, so next, so from the figure that's shown is there are two figures. So for the left one is so for circuits where it is necessary to remove or null the offset, many op-amp chips provide two pins that enable this to be done. So using the offset null adjustment requires a potentiometer with its wiper connected to the negative supply with some op-amps or to a zero voltage with others, so it is necessary to check the data sheet. So the value for the potentiometer may typically be around 10 kilo ohm to 100 kilo ohm. But again, when undertaking the electronic circuit design, check the data sheet for the most suitable value. So, alright, so this the left one is the figure on operational amplifiers with an offset null capability. 2 pins are provided as shown. So the right one is I will elaborate it, which is to incorporate an offset null capability within the operational amplifier. A number of different actual circuits can be adopted. So this is an example. So the op-amp offset null circuits adds a balance capability to the input circuitry as shown in the example of the op-amp input stage. So the op-amp's offset null connections enable the input circuit balance to be obtained by applying external circuitry. So operational amplifier offset null capability is used for applications where DC amplification is required. So the small offsets caused by the input circuitry are amplified and is left unchecked. They can become an issue. So one of the major areas where the offset null capability is used within instrumentation and sensor applications. So here small DC change need to be monitored, and op-amps provide the ideal way of amplifying the DC voltage before they are measured or converted to digital formats. So as such, the offset null capability is essential for the operation of these circuits. So the most straightforward for applying the offset null is to use a simple potentiometer, but increasingly digital feedback is used and the value is measured and set automatically by the system. Nevertheless, the same principle is used within the op-amp. Alright, so for the next one is frequency compensation. Alright, so op-amps may become unstable sometimes, and to make them stable for the entire frequency, bands cap is usually connected between its drop pin 8 and pin 1. So usually about 47 picofarad this capacitor is added for phase compensation, or we call it as frequency compensation, so that the op-amp will remain stable. So the major challenge is to improve the stability of an op-amp in a wide bandwidth of applications. So the solution is to compensate the amplifier in terms of frequency response by using a frequency compensation circuit across the operational amplifier. So the stability of an amplifier is highly dependent on different parameters. So there are actually different types of frequency compensation techniques used in electronics. So this is one of the example, which is the figure shows the circuit used in dominant pole compensation technique. So this technique uses a simple RC network connected across the output of the operational amplifier circuit. So a sample dominant pole compensation circuit is shown above. So this works great to overcome the instability issue. Alright, so for the last one is feedback. So in the diagram shown is where the signal is applied to the non-inverting input, and in inverting input is connected to the output. So V plus equal to V input and V minus equal to V output. So therefore, V output equal to 10,000 times to the V input minus V output. So hence the output voltage is almost equal to the input voltage. So we can see that actually there are two types of feedback, which is negative feedback and positive feedback. So the negative feedback is where the output of the op-amp is connected to its inverting input, which is -1. So thus the output is fed back to the input so as to reach an equilibrium. So thus the input signal at the non-inverting plus input will be reflected at the output. So the op-amp with the negative feedback will drive its output to level necessary, and hence the voltage difference between its inverting and non-inverting inputs will be almost zero. So for the positive feedback, whereas the output voltage is fed back to the non-inverting plus input. So the input signal is fed to the inverting input. So in positive feedback design, if the inverting input is connected to the ground, then the output voltage from the op-amp will depend on the magnitude and polarity of the voltage at the non-inverting input. So when the input voltage is positive, then the output of the op-amp will be positive. And this positive voltage will be fed to the non-inverting input, resulting in a full positive output. So if the input voltage is negative, then the condition will be reversed. Alright, so that's all from us. Thank you for listening.